Now we introduce guided policy search using Bregman alternating direction method of multipliers. For the policy search method, the original problem is to find the policy pi by solving a constraint problem, minimum the expectation loss along a trajectory subject to a constraint. That means when we get the minimum, make sure the policy we search has the same distribution as the system controller for any stage, action, and time. So the constraint problem above can be formulated as a Lagrange. Then we can solve it by using dual gradient descent method in primal and dual spaces. So to solve this problem, because deeper visual motor policy is a end-to-end method. So we need to combine this original problem, first convert to become a Lagrange. Then we need, it includes two steps. One is for the trajectory optimization. Another one is the policy optimization. So we need to combine these two steps in one procedure. That's kind of a Bregman alternative direction method of a multiplier. So the BADMM has the following Lagrange formulation with regard to the parameter theta related to the policy network, and the P is the system controller. So we have two objective functions. One is for the policy optimization. Another one is for the trajectory optimization. And here lambda is a Lagrange multiplier. So in this during the derivative of this two formulations, we modify the constraint a little bit, divided by T at both sides. So that means here this uses the chain formula, chain rule. We can this T equal to this, and here they say keep the same format, just divided by the P. And use this way, actually, we first we keep the expectation loss, and then we plus expectation of the multiplier on this distribution and the multiplier on this direction plus key error divergence. In this way, we solve this objective function and this objective function. Finally we get a convergence result. And here in the for the objective functions, the two function phi, one is related to network policy parameters, another one is a controller. So they can express as expectation of the this policy and this controller. And by in this formula we keep we optimize the theta. We need to remove the terms no relation with theta. Same thing to the second objective function. We remove the term with no relation with the P. So we get the two formula, and once we get the P and the theta, so we get the policy and the controller, and then we can update the multiplier. Once we got the stable and convergent multiplier, then we get the convergent theta and the p. Of course, our goal is to get the theta. Once we get the theta, we can know exactly our policy network. Then for given observation, we can predict the action to control the robot. And for the two steps, one step, as I mentioned previously, is trajectory optimization. For example, if we know the system dynamic, we can, once under this policy or use this controller, take this action, we know exactly what's the next state based on this knowing system dynamic. But in most of the case, we don't know accurate system dynamic. So we, suppose the guided distribution is Gaussian. So we can express the dynamic and the controller as the time varying linear Gaussian. I'm saying in this formulation, this is Gaussian distribution, and this is also Gaussian distribution. Because we don't know exactly the system dynamic, always at this state, we based on this controller takes this action, we just not directly go this guided state. We just basically go to use the previous use the state, get the previous iteration, then we set up a small difference. We make sure these two pi hat and the pi and the p hat and the p, we make sure the KL divergence is smaller. This is a small number. So when convergence, we can make sure the policy we search is equal to the controller. This is for the trajectory optimization and unknown dynamic. This is unknown dynamic. And another step is the supervised policy optimization. Supervised optimization, that means once we use the trajectory optimization, get the convergent controller, we can use this controller as the target to train our policy network. And because both the controller, we assume both the controller and the policy we will learn is the Gaussian distribution. So we can express the Gaussian policy in Gaussian distribution from the mean and covariance. So based on this simulation, we can express the objective function for the policy parameter theta. We get this one. This is for the controller. This is for the policy, and make sure their expectation loss and plus. This is their squared difference plus this part is related to the Lagrange multiplier. We together to get the objective function. So once we get a convergent result, so the policy we learned is the same as the system controller P. And then for the example, for the case, never appeared in the train data set. Use this policy, we still can predict the correct trajectory, reach to the correct terminal state. For more details, can check with these references. Thank you. Bye.